Okay, guys, welcome to today's lesson in statics. Today we're going to be covering problem 99 from chapter 2. So problem 99 says, 3 cables are used to tether a balloon as shown. Determine the vertical force P exerted by the balloon at A, knowing that the tension in cable AB is 259 newtons. So first thing I'll do is start by drawing a free body diagram. So first off, we have our point A. It has a tension force going down to this tie at point B. We have our tension force from A going down to point C at stake C. And finally, the stake in the ground from tension going from A to D is drawn as well. Now finally, don't forget the force. The problem says there's a vertical force P exerted in the Y direction, going vertically. So it would be on the positive y-axis. It's trying to pull the balloon up. Okay, that would be our force P. It's in tension. So remember, we draw all of our tension vectors going away from the center of the free body diagram. All right. Next thing we're going to do is find the position vectors going from A to each one of these stakes in the ground. So I want to find my position vector from point A to B, label it R for position vector. Now notice, look at its components. Okay, if we look here, A is going from B, A is going to B, and the x direction is going on the negative x-axis, and the negative x direction, 4.20 meters. So it would be negative 4.20 meters in the I hat direction. Next, don't forget we have the y direction. It's going down to the ground, negative 5.60 meters in the j hat direction. And then notice stake B is on the x-axis, so there is no direction, there is no dimension, no position vector for the k hat direction. So let's write plus 0 meters k hat to remind us that there is no component in the z direction. Next, we're going to calculate the magnitude or the distance from A to B. You can represent this as RAB or simply distance DAB, either way. So we're going to take the square root of each one of these components squared and add together in parentheses. All right, so first we'll have our negative 400.20 meters squared plus our negative 5.60 meters squared. And then we can leave out our k hat vector since it's 0. So when we do this, type in the calculator, we have in parentheses negative 4.2 squared plus in parentheses negative 5.6 squared. We're going to put that in parentheses. And we get 49. We know the square root of 49 is going to be 7, so it'll be 7 meters for our distance for tension and position vector from A to B. Okay? Knowing that, we can also write down our equation for our tension vector from point A to point B as being equal to the scalar tension magnitude, the value they gave us, which was 259 newtons for tension AB. Go and put that in my figure diagram to remind ourselves. So we have our tension as being 259 newtons from point A to point B. Okay, so we have our scalar tension value that's given to us. And then we have, in our equation, we have this multiplied by the position vector, R, A to B, and then divided by the distance, or the magnitude, of that position vector. This is, as you recall, our unit vector, A to B. So, substituting these values in, we have 259 newtons. We have our distance, we know is 7 meters. And we have our components, we know as negative 4.20 meters minus in the I hat direction minus 5.60 meters in the j hat direction plus, again, we can leave this out, but we'll go and include a 0 in our k hat direction. Okay, so our tension value, our tension vector from point A to B is going to be, as we multiply this out, 259. Go ahead and clear the screen. Go ahead and actually move this calculator up a little bit so we can all see. Okay, we have 259 divided by 7, which is 37. So we're going to multiply all of these values, each one of these x, y, and z component values, by 37. So 37 multiplied by negative 4.2 gives us a negative 155.4 Newton value in the I-hat direction. Multiply 37 times negative 5.6. That gives us a negative 207.2 Newton value in the j-hat direction. So we have our tension value for vector A, B, for the tension vector from going from A to B. We're going to do the same thing for point AC, or I should say vector AC, and then the same thing for our tension vector A to D as well. So, moving along, all right, let's go ahead and do our position vector from A to C. All right, so it's going to be, if we notice, in our x direction, we're going from point A, which is vertical above the origin. We're going from A to C, we're going positive 2.4 meters. In the I-hat direction, positive I-hat direction. All right, we're going, again, down negative 5.60 meters in the j-hat direction on the vertical axis. And in the z direction, we're coming out 4.20 meters in the z-axis. So plus 4.20 meters in the k-hat direction. We'll do the same thing, calculate our magnitude of our position vector, our RAC value, as being the square root of each one of these components in parentheses squared and added together. So we have our positive 240 meter component squared plus our, in parentheses, our negative 5.60 meter component squared, and then plus, again, our positive 4.20 meter component squared. And we're going to calculate this value now. So we're going to go back down, bring the calculator up. Okay. Go ahead and clear the screen real quick. So we have our 2.4 value squared plus our negative 5.6 value squared plus our 4.2 value squared. We don't need to square the positive values in parentheses, only the negatives must go in parentheses. So we take the square root of this number. Oops, my mistake. Delete that negative out of there. So the square root, we get 7.4. So our magnitude of our distance now is 7.4 meters for the cable AC. The distance from point A to point C we know now is 7.4 meters. Okay, we can go ahead and continue and find our tension vector for AC now. So we know, same equation, our tension value for AC is equal to tension scalar value AC multiplied by the position vector R from A to C over our distance R A to C. So we substitute these values in. We don't know tension AC. We're going to calculate that though soon. We do have our position vector, and we have our distance of 7.4 meters. So I'll put my distance right here, 7.4 meters right here. And then I'm going to multiply this all by our position vector AC, which is 2.40 meters in the I-hat direction, minus 5.60 meters in the j-hat direction, plus 4.20 meters in the k-hat direction. Okay, we can simplify this a little bit. If we divide each one of these values by 7.4, we get our tension AC. And the I hat direction is going to be multiplied by, let's see, 2.4 divided by 7.4, which would be approximately 0.324 in the I hat. We'll write these vertically now to save space. Minus, so we have negative 5.6 divided by 7.4, which is going to be negative 0.75, rounding 7 in the j hat direction. And again, these were meters. These are units of meters. It's okay if we leave those units off every now and then. We want to remember that those units are there for meters. And then finally, we have our value of 4.20 meters divided by 7.4, which is going to give us a positive value of 0.568 meters in the k hat direction. Okay? So, also remember we have our units off here. We should put our units here, but it's okay if we don't put them here. Just remember there are units of meters here as well as here for each one of these components. They will, in fact, cancel, so it's okay as we leave them off. Okay, now we're going to also do the same thing and find everything we just found for A and B, cable A and cable B, AB and AC, for cable AD. Okay, so let's look at the diagram again for the balloon. All right, so we have cable AD. Notice it's on the z-axis. All right, so notice that means we have no x-axis or I hat component. It doesn't move in the positive x direction or backwards in the negative x direction. The stake is at 0 in the I hat direction. So our RAD vector, our position vector from A to D, will be 0 in the I hat direction. We're going down again the same distance, 5.60 meters in the J hat direction for the y-axis. And then notice we're moving in the negatives. On the negatives, here's positive z-axis. We're moving on the negative z-axis a distance of 3.3 meters. So we're going backwards 3.30 meters in the k hat direction. Okay, we're going to find the distance again. So our distance, RAD, will simply be the square root of each one of these components squared and added together. So we have 0 in the I hat. So we have first component will be negative 5.6 meters squared plus negative 3.3 in parentheses meters squared. Okay, and this will give us a distance value. If we plug this in the calculator, let's go ahead and clear our screen. We can go ahead and bring this calculator up again. Okay, so we have in parentheses negative 5.6 squared plus, again in parentheses, negative 3.3 squared. We're going to take the square root of this number, and it gives us 6.5. So this is 6.5 meters is the distance in cable A to D. Okay. From here, we need to use our summation of forces. Knowing that we're in static equilibrium, we're going to apply our summation of forces being equal to 0 to solve for the components of the tension in cable AC, cable AD, and then we're going to use those components to calculate the vertical force upward that the balloon is pulling on point A. All right, so the first thing I would do is I would notice, if I look in my I hat direction for each one of everything I calculated, I know the I hat value here for AB. I know the I hat value for AD, cable AD is 0. Okay, and I'm going to find the tension in cable AC. Let's actually go ahead and calculate vector AD real quickly before we do anything else. So let's see, cable tension AD would be the tension AD scalar value of the tension, we don't know yet, multiplied by the position vector RAD over the distance, magnitude of that position vector, the distance RAD. So that'd be equal to tension AD divided by the distance we just found of 6.5 meters. And then we're going to go ahead and multiply by our position vectors we know. 0 I hat minus 5.6, 0 meters j hat minus 3.3, 0 meters in the k hat direction. We can go ahead and simplify each one of these by knowing tension AD is going to equal, let's see, we go ahead and say we divide negative 5.6 by 6.5. 5.6 divided by 6.5. So we get a value of negative 0.862 times tension AD. And then we have, don't forget that's in the j hat direction. There is no I component for tension AD. And then we're going to divide negative 3.3 by we're going to divide negative 3.3 by 6.5, or distance, and it gives us negative 0.50, rounding up 8 tension AD in the k hat. Okay, so now going back to what I was saying just a minute ago, as far as involving the unknowns, we know the component for tension AB. We do not know the tension component for AC, and there is no tension component in the x direction or in the I hat direction for tension AD, which means there's one unknown, tension AC, if we were to sum force in the x direction. So let's go ahead and say we're in static equilibrium. The vertical force P is acting up on the balloon. Okay, so we're going to say our summation of force in the x direction is going to tell us, see, let's separate this previous work from what we're doing now. This is all summation of forces. So we're going to say, all right, we have negative 155.4 newtons in I hat direction. So this is all in the x, sum of force in the x, or in the I hat. Sum of force in the x and the I hat, same thing. We would have negative 155.4 newtons. And then our tension AC component is 0.324 I hat times tension AC. So we have plus 0.324. Oops, we're losing the focus. Into frame. So our summation of force in the x direction is 0. We have our tension AB, negative 135.4 newtons in the I hat direction, plus our 0.324 times tension AC scalar component in the I hat direction for that. And then tension AD has no component in the x or the I hat direction. So we're taking our tension AB in the I hat, our tension AC in the I hat, and then there's 0 in the I hat for AD. So we have 3.324 times tension AC, and that is equal to 0. As we know, our summation force in the x equals 0 because we're in static equilibrium. The balloon is not moving currently. There's a force acting trying to pull it up, but it is not yet moving. Static equilibrium. Okay. So now it's a matter of solving for tension AC. We're going to move this 155.4 newtons over to the right. So we have 0.324 tension AC equals positive 155.4 newtons. We're then going to divide both sides by the 0.324 coefficient in front of tension AC. So this will give us tension AC as being equal to, one second, tension AC will now calculate as we'll calculate this as 155, one second. So we'll calculate this as being 155. It's 11. Let's see, 155.4 divided by 0.324. Okay, and for this value, we get 479.6. We can round this up approximately to 480. I'll keep it as 479.6 newtons for now. Okay, now notice we have our value for tension AC. We can substitute that in to each one of these components and find the value of the force, the tension in each one of those components in the x, y, or z direction. So now if we notice, we have tension AC. All right, we have our j hat direction, but there's an unknown force, a P, pulling up as well. So we need to find tension AD next. To find tension AD, let's go back to the diagram real quickly. The diagram shows us that tension at stake D, point D, is along the z-axis, remember? So that means there is no I hat component. There's no I component. So we can use this value now to calculate tension AD if we were some forces now, not in the y direction yet, but if we were some forces in the z or k hat direction. So now sum of forces in the z direction being equal to 0 will give us tension AD. Okay, so let's look at our forces we have. We have our tension AB. Well, there's no component, there's no k hat component, so it would be 0 in the k hat direction, the z direction for AB. AC is going to be, we forgot to write in the tension AC multiplied by each one of these components here. So this would be tension AC is, let's just put this in a big parentheses. Tension AC is multiplied, remember, by this value and by this value. Okay, so it would be plus 0.568 tension AC in the k direction, and then we know this value. This is 479.6, so we can substitute that in as well. So we can go ahead and write this in as being times 479.6 newtons. And then the k hat direction for tension AD, it's minus, in the z direction, minus 0.508 times tension AD scalar value. And that is equal to 0, since our sum of forces is equal to 0 in our k direction. So when we go this again, just bring this in the frame. We have 0 k hat direction for tension AB. We know our value for tension AC comes from this component here. And then finally, tension AD comes from our k hat component here. We're summing force in the z direction. All right, so if I were to multiply now 0.568 times 479.6, that gives me 272.4128. If I can move that over to the side, this is equivalent to 272.4.4. So if we move this over, or move this over, make it positive, we'll have 272.4 newtons equals positive 0.508 tension AD. We divide both sides by 0.508. That coefficient's gone. That tells us tension AD would be equal to, equivalent to this number divided by 0.508, which is approximately 536.2 newtons. Okay, so now we're going to sum our forces in the y direction. We're going to find out the value of force value of the p vector. going on. So in the y direction, we'll have P pointing straight up, be positive, and we'll have our y components, or Ji components, of each one of tension AB, tension AC, and tension AD, we've now found pointing down. Okay, so moving on, we have summation of forces in the y-hat direction, or the y direction, should say. All right, that will tell us what vector P is equivalent to. The magnitude and direction we know is vertical. All right. So summing force in the y direction, we know we have a 207 Newton force in the negative j direction for AB. So we have negative 207.2 newtons in the j direction. These are all coming from the j direction for the y forces. We have a value of, let's see, 0.757 times the force value, 479.6 for AC. Okay, so and it has a negative component as well. They all should for each tension in the cable is pulling down on the balloon. 0.757 times 479.6 newtons. And then finally, the tension AD has this component, negative 0.508 times tension AD, we just found is 536. It would be minus 5.08 times 536.2 newtons. And then, of course, our force P, pulling straight up, the vertical force P, and this is all equal to 0, as all of our forces sum to 0 is when we're in static equilibrium. So now to calculate P, I'm going to simply move P to the other side, making it negative P in the next step, and then calculate what this number is, and then we'll be able to divide by -1 and determine what the value of P is. All right, so my calculator, I have 207.2 minus 0.757 times 479.6 minus 0.508. My coefficient should all the small decimals. 0.508 times 536.2. And that's going to equal to negative P. So negative P is negative 428.2 newtons. So if I then divide, one sec there, guys. One mistake I just made. I used the k-hat. Notice I used the k-hat coefficient instead of doing j-hat, we're doing y, force and y. So it would be negative 0.862. I apologize. So we're going to go ahead, go up here, show you a little trick, and grab this, and we can go back and edit it and change it to 862. Okay. And notice we also need to make this a negative in the calculator. That would help as well. So we're going to go ahead, copy this over. All right, so we're going to start off negative 207.2 minus 0.757 times 479.6 minus 0.862 times 536.2. And now we get our correct answer as being equivalent to negative 1,032 newtons, which, remember, is negative. P is pointing up, so our p-hat vector is equal to positive 1,032 newtons, and it's going straight up in the vertical axis. Thank you and have a good day.
All right, guys. Thanks for joining me in another Simple STEM Solution video. Be sure to like and subscribe. Also, if you'd like to support this channel or have particular questions you want answered, be sure to check out my Patreon community via the link in the description below.